This video is looking at rates of reaction and is a review of C5 for GCSE and the very basics of rates of reaction for A-level. So first we need to understand what we mean by rate of reaction. Whenever we talk about the word rate in science, the word rate means something, and it means divided by time. So in essence, what we're looking at is how fast reactions occur within a certain period of time. And one way of measuring rate of reaction is if we do an experiment where we have magnesium ribbon and we add hydrochloric acid to it, as an example, we're going to have magnesium plus HCl, and we will make magnesium chloride as our salt and hydrogen gas. Okay, and then the hydrogen is a useful bit because I can measure the volume of gas that is produced, and I can use the equipment as suggested. So I need a conical flask to do my reaction in, a bung and a delivery tube, and then this piece of equipment which is a gas syringe, and that we can use to measure the volume of gas that is produced. If I then plot that as a graph, it will look something like that. Okay, so this is a volume of gas against time graph, and the gradient of this line, which is how tall it is, so this is the change in y divided by the change in x, how wide it is, okay, will give me my gradient. So my gradient is equal to the rate of the reaction and is equal to change in y over the change in x. How tall it is divided by how wide it is. The units will be the y-axis divided by the x-axis, so the units for rate in this case would be centimetres cubed / seconds. Okay, but if this was in minutes, it would be centimetres cubed per minute. Okay, so the gradient of my graph allows me to work out the rate of my reaction, and you can see that it's steepest at the start. So the reaction occurs faster at the start, quite simply because you have more reactants, and as you use up your reactants, you can see the rate of the reaction decreases. The gradient's getting less steep until we get to a point where it plateaus, and when it comes flat at this point here, this is when the reaction has stopped. Okay, so when the reaction plateaus, becomes perfectly flat, then the gradient is 0, the reaction has stopped. So that's one way that I could determine rate of reaction. Another alternative would be I could use a conical flask again, but this time I would be measuring same reaction, okay, magnesium ribbon and my hydrochloric acid, but I could instead put it on some scales, okay, and then I could measure from the scales, okay, how many grams that is, and I would measure the mass loss in this reaction. And the reason is because now the hydrogen, the gas, is free to escape. So as the gas escapes, the mass decreases. If I did this reaction with the bung in, the mass would remain constant because the gas would be trapped, but the pressure inside here would increase. So because there is no bung in this case, the mass can be lost, and I can measure the mass loss and do a graph of mass loss against time. But since most gases are quite light, that doesn't give us, it's more difficult to measure that than doing this version of the experiment. But I could do the same thing and my gradient would still give me an indication of my rate. In other words, how fast my reaction is going. Another experiment for you to be aware of is the Thiosulfate Cross experiment, which again, we use a conical flask. But on the Thiosulfate Cross, we have a piece of paper underneath with an X drawn on it. Okay. And as we do the thiosulfate cross reaction, what happens is we produce colloidal, which just means solid particles suspended in a liquid, sulfur. And the sulfur will block the X from being visible. So if you are looking at it from above, then the X will disappear. And what you can do is measure the reaction time for how long that takes for the cross to disappear. And it's important to understand that obviously the longer it takes, the slower the reaction is going. So we can say that reaction time is inversely proportional to reaction rate. In other words, the longer the reaction takes, the slower the rate of the reaction. The shorter the reaction time, the faster the rate of reaction. So it's being used up. So the thiosulfate cross is another example, and this utilises the timing method to work out an endpoint. So we've got 3 experiments that we could use potentially to determine rate, and we've got our basic graph, the gradient of which is equal to the rate. So what we now want to know is what affects rates of reaction, and there are 5 factors that affect rates of reaction. So the first one is temperature. If I have a higher temperature, my reaction will proceed at a higher rate. Next, we have catalysts. We then have concentration and pressure together. The difference is only that concentration applies to liquids and pressure applies to gases. And then we have surface area, which obviously is applicable to solids. So let's look at these 5 factors and how we'd explain them. Now, the key phrase that we always come back to when it comes down to rates of reactions is the idea of successful collisions, because in all chemical reactions we have to have 2 particles at least that are going to collide with each other, and when they collide with each other they can react, right, or they can bounce off each other. It depends on whether this successful collision results in those molecules joining, those molecules breaking, reforming in different arrangements, or whether they are unsuccessful and just bounce off each other and go out in different directions. So we're looking for always this phrase, successful collisions. So every answer that we end with when we're explaining rates of reaction will end with this phrase. Okay. Now, temperature, by increasing the temperature, what we're doing is we're increasing, firstly, the kinetic energy and the speed of the actual particles. So if we increase the kinetic energy of the particles, it's more likely that a greater proportion of the particles will have enough energy in order to react. We call this energy the energy of activation. So with temperature, the first point is more particles with energy greater than the energy of activation. Okay. The second point is that because they're going faster, they're going to collide with each other more frequently. So we increase the frequency, which means the number of collisions every second of successful collisions. Okay. So with temperature is a good one to start with because it's these 2 points that we're going to use frequently. Are we affecting the energy in terms of the energy of number of particles with energy greater than the energy of activation, or are we affecting the frequency of the collisions? So temperature does both. If you're asked to explain a catalyst, what a catalyst will do is it won't affect the frequency of collisions. A catalyst will lower the energy required to initiate the reaction. So all reactions have a starting energy for their reactants. You put some energy in for a typical exothermic reaction, and you get some energy out of your products. And the energy that is required here, this is our energy of activation. How much energy is required to start a chemical reaction? If you use a catalyst, what happens is we provide a lower energy of activation by providing an alternative route for the reaction to occur by, right? So we're reducing the energy of activation. So we reduce the energy of activation by providing an alternative pathway for the reaction. And quite often that's the surface. It's important to know one other main thing about catalysts, which is that catalysts are not used up in the process of being used. So if you add iron in the Haber process, iron isn't used up in the reaction. Catalysts can be recovered. They are unchanged overall by the chemical reaction. So that's important that catalysts aren't used up and overall they aren't changed. They just speed up the rate of the reaction by reducing the energy required, and therefore more particles have energy greater than the energy of activation. for the last 2 points, I'm going to group these two together because concentration and pressure is always explained with 2 points. Firstly, what we mean by concentration and pressure. So you have to first of all consider two volumes. If I've got a low concentration, it means that I've got a small number of particles in that volume. And we have to say volume because it is, after all, three-dimensional. Okay. Whereas if I have a high concentration or pressure, then I have a lot more particles in that same volume. So first you explain what concentration or pressure is, which is the number of particles per unit volume. How many particles you have for each centimetre cubed of space that you've got. And then just by having more particles in a certain number, certain volume, what that leads to is an increase in the frequency of successful collisions. Remember, frequency just means the number of collisions every second. Surface area is explained in exactly the same way. The difference of surface area is that if you imagine you've got a lump of chemicals, right, the solid, the other chemicals can only collide with the surface like that. If, however, I break that up into smaller lumps, now not only can they attack the outer surface, they can also attack the inner surface as well. So we've increased, by making it go from a lump to smaller chips or smaller chunks, and then we could take that one step further to a powder, we increase the surface area. So powders have a greater surface area than solid lumps because you can get to all of the internal particles as well as the external. So again, by enabling there to be more of the solid surface in contact with the other reactants, we increase the frequency of successful collisions. And if I just show as an example, if I, instead of using magnesium ribbon for this reaction, if I used magnesium powder, then what would happen is my rate of reaction would increase, so this line would become steeper. I wouldn't make any more stuff though, so I would still end up making the same amount of product, the same amount, total amount of gas. I'd just make it quicker, so my line would be steeper. So this would indicate powder, which has a higher surface area and hence a faster rate of reaction. So all of the stuff on here is the absolute basics of rates of reaction that you need to know. You need to be confident with explaining any of the different rates of reaction. All of them come back to how we affect the successful collisions. Either the energy of the collisions, so temperature and catalysts both affect energy. If you increase the temperature, you give the particles more kinetic energy, which means more particles have more energy than the energy of activation, whereas catalysts reduce the energy required to initiate the reaction. They reduce the energy of activation by providing an alternative reaction pathway, and they aren't used up. And then frequency of successful collisions is perhaps the most important and useful phrase that you can learn, because you can see that we use that to explain temperature, we use it to explain both concentration, pressure, and surface area. So if you can remember that phrase, and remember the only one of these 5 things that doesn't affect the frequency of successful collisions is catalyst, you can very easily pick up marks on this bit. You should be aware of the 3 methods of determining rates of reaction, either by collecting gas, by measuring mass loss using some scales, or by using the Thiosulfate Cross to determine an endpoint. Remember that reaction time is inversely proportional to reaction rate, and if you've got a graph, the gradient is the rate of reaction. It stops when it plateaus, and the steeper the line, the faster the rate.